lecture, we continue calculating the scattering amplitude for a process. We have this simple model where we have two kinds of particles, type 1 and type 2, and they interact through such a potential, which essentially tells me that I can create two particles of type 1 and annihilate one particle of type 2. Well, here there are various options. If you just write these phi 1 and phi 2 fields in terms of annihilation creation operators, and you will see what particles can be created and annihilated. And in our case, where we start with two particles of type 1 and two particles of type 2, there were essentially two kinds of processes. One in which both of these particles are annihilated, and the second kind of particle is created. And separately, these two of the first kind of particles are created, these two diagrams over here. And there was also another contribution where both of these particles, one of them emits the second kind of particle, which is absorbed by the other one, or the other way around. We just looked at these two cases explicitly. In principle, if you want to calculate the full amplitude, you have to calculate all these four contributions. We looked at these two cases, and at the end of the day, we introduced this notation of contraction. Basically, the idea of calculating each one of these diagrams is you write your states explicitly in terms of the creation operators, and then when you write your matrix elements over here, in terms of a matrix element of the vacuum, you just try to move all the creation operators to the left and annihilation operators to the right, because the annihilation operator acting on the vacuum from the left gives me 0, or a creation operator acting on the vacuum from the right also gives me 0. So as we are moving them all around, this was the notation we use, this line, that basically tells me that corresponds to the contribution in which I commute this phi 2 operator with the creation field, or the annihilation field in this case, since it's a bra, of this phi k5 state. This is basically a shorthand notation. And then when we did all these computations, we had two contributions. Basically, we had these two contributions, because you see, in each one of these cases, either one of them emits the second kind of particle, or the other particle emits the second kind of particle. We have different intermediate states, different in the sense that the energy will be different. Here, we denoted it as En1 and En2, those are the energies. And at the end of our computation, we obtained that this was, okay, where was it? Okay, this is what we obtained. Forget the numerator for the time being, it will be cancelled by some normalization. But if you look at the denominator, there is this K5. By the way, up to this point, when we have this intermediate state of one kind of particle and one type 2 particles, the energy momentum relationship is always the energy is equal to momentum squared plus the mass squared for all of them. Whether it's the intermediate state or the external states, everything has energy equal to its 3 momentum squared plus its mass squared. But then, just to simplify the notation mainly, we introduced a 4 vector. This already we know that this is we have the 3 momentum conservation at each vertex. So for this diagram at least, we have the 3 momentum of my particle is given by K2 minus P2. Remember, K2, I can always promote it to a 4 vector. Just the energy and K2 together, they make the 4 vector, and similarly for P2. So then I define the 4 vector K5 by defining K5 0 as the differences in the energy of K2 and P2. So this was a new 4 vector that kind of, let's say, we invented just to simplify the notation mainly at this moment. And with this new 4 vector, this is what we have in the denominator, m squared minus the 4 vector squared. But this 4 vector k5, you see, my particle has an energy, omega k5, what we call omega k5. This one, this is my omega k5, which is the free momentum squared plus the mass squared. So if you would calculate omega k5 squared minus k5 squared, you always get m2 squared. But now I'm defining a different zero component for this 4 vector, which is k5 zero. And since this is not equal to the energy of my particle, k5 zero squared minus 3k squared, or this k5 squared, 4 vector squared, is not equal to the mass of the particle squared. Yes, we are kind of inventing this 4 momentum. We are assigning this 4 momentum to my particle still, my intermediate particle. Its 4 momentum squared is not its mass squared. Usually if you have a particle, its 4 momentum squared is equal to its mass squared. So we make this distinction. We have particles, let's say, which have 4 momentum squared is equal to their mass squared. This one, let's say, whose 4 momentum squared is equal to mass squared. This is what we call on-shell particle. And we have other kinds of particles which will have this assigned 4 momentum squared is not equal to its mass squared. These are called off-shell particles. And so these particles that appear at intermediate stages, like here or here, well, it's usually shown in this form. They're assigned 4 momentum, assigned in the sense that we invent this 4 momentum so that we impose at each vertex 4 momentum conservation. Our formalism here only tells us that 3 momentum is conserved at each vertex, but we just invent this 4 momentum. This new 4 momentum is conserved at every vertex, but since because of these conditions, because of the way we define this, but the 4 momentum squared is not equal to my mass squared. And the terminology we will use is these are so-called virtual particles. Virtual in the sense that they never reach our detector. If they reach our detector, then we cannot do this. They just appear at an intermediate state and disappear at some later stage in our computation. They should disappear. So this is what we mean by virtual particle. But I would like to still emphasize that if I would like to talk about the energy of this particle, energy is h3 momentum squared plus m squared. It's just the zero component of this momentum is not equal to the energy of this particle. So any questions up to here? That is where we had left.
I have a question. So when we, in the beginning, when we write the potential itself, it actually defined, at least for field theory sense, defined an interaction, right? Interaction between fields. We added to our free theory, so we try to solve it. But let's say we work on some scattering problem. In their potential are most likely not something local, right? It's like we are defining a region and a particle when it comes near that region, it just scatters from that region. Let's say we can assume sphere-like region of other geometries. Or at least we can put some Dirac delta so that at that point there will be some kind of scattering. But in here, we are evaluating the potential at the same point. So all the fields are at the same point. And from the scattering perspective, like how can we see this potential so that what kind of, what should we understand from this potential? In here, all the fields are at the same point and we are integrating over all the space, so that means it's just somehow, right? It's just a number because there are no different other dependencies. But if you like to solve some scattering problem, most likely our potential will be, let's say, easiest case, V0 Dirac delta, so that we will put it inside our Born approximation and solve it.
If you have a Dirac delta potential, that's effectively this one. Everything is at the same point.
Yes, right? So we are putting Dirac delta actually, potential actually, something like that. Is that a good analogy?
What do you mean by potential? let me start by asking that question first.
For me,
Yeah, I mean, you are saying that there will be this potential which will act between particles from a distance. What do you mean by a potential?
I mean it can be some physical matter that we can just model it in terms of.
Forget about the modeling. I mean, first, if we define what the potential is, then we can work on modeling it.
Okay,
In the sense that you are using it.
It's something that allows interaction between fields.
Okay. Well, you see, here I have an interaction between two of the type 1 particles. You see, what you will see at the end of this, by the way, the midterm, just a reminder.
In class hours, right?
Yes. Well, you see, in the process we studied, what happened? We had two particles having the same some momenta, and after some time, we had two particles having different momenta. They did scatter. So here we have a scattering problem. Scattering problem described in terms of local interactions.
This scattering problem.
This is a scattering problem, which we calculated the amplitude of, half of the contribution to the amplitude, let's say. And we used, well, this was the potential we used. Well, if you want to find some non-local potential, let's say that we have a system of charged particles, and we would like to write their electromagnetic interactions, electrostatic interactions or electromagnetic interactions. And we don't want to use this photon description. I don't want to invent some new particles. I just want charges interacting with each other by this action at a distance. Well, how do you write the electrostatic potential energy for such a system? Well, let's see. We have some charge density somewhere. This is charge density of my system, let's say, around R1. This is the charge of a very small volume around that R1. Then I have some other charge at some different point, rho of R2. So these are just 2-point charges making my system. Well, they are, the potential energy between them will be 1 over R1 minus R2, if you like. Then if I sum over all the charges of my system, now let me move this one also to the front. This is my V. Well, what is rho? We had calculated the number density operator. For example. So this is one interaction between, this is a so-called a non-local interaction between the particles. What is the Laplacian of 1 over R1 minus R2? Yeah, it's the 4 pi Dirac.
Some 2 pi something.
4 pi Dirac delta R minus, let's say R0. Well, this is not Lorentz invariant, etc. We have all the problems, but well, here we have a potential. Well, do you remember what we had obtained for our scattering problem? The corresponding amplitude was lambda squared 1 over K5 squared minus M2 squared. Again, just forget the denominator. Let me just look at that. Forget the numerator. Let me look at that denominator. It has this form. Or let me write it this form. Well, this is in momentum space. If I would write this in the coordinate space, this would be where this operator is del mu, inverse. What is the inverse of an operator? Well, it is something that satisfies this equation. Is equal to 1. This is an operator form, let's say. I can talk about I can just go to the coordinate basis, take the various matrix elements, etc. This is just so what is actually happening here is, I mean, you can have various perspectives, but basically this particle is creating some kind of a potential, and the other particle is interacting through this potential. This 1 over p squared minus m squared is nothing but basically this term. Of course, since it's massive, it's not just 1 over r, there's the exponential one. This g e to power minus mr divided by r. Well, I took a couple of steps. First of all, I looked at the three-dimensional case. I just set P0 equal to 0. And then Fourier transforming gives me the potential. You see the Fourier transform of d cubed r e to power I q r this is the Fourier. Do you know how to calculate this Fourier transform? Try it. Okay, let's look at the scattering problem. Let's start with the classical problem. We have some kind of a potential over here, a source, something that creates a potential. And we are sending particles. You can just think about the Coulomb potential. There's let's say, a point charge at somewhere here. Then you send some other particle. You can just think of the Rutherford's experiment, for example. There was the nucleus, which was positively charged, the gold nucleus, and he was sending the alpha particles. And due to their repulsion, these particles scatter, they change direction. Eventually, they move in this in a different direction. Here, of course, I'm assuming that the other particle is fixed, so there's no energy change. That's why here in this derivation, to obtain this one, I set energy equal to the zero component equal to 0, because there's no. I'm looking at the process in which there is no energy change to determine the potential energy. So this is the initial direction of my particle. This is the final direction that my particle is moving. So this is called the scattering angle. And this is called the impact parameter, B. Why are we looking at the scattering problem? Well, basically everything we observe, we measure is a scattering process. For example, when I look at there, I see that there is a blue chair over there, and what is actually happening is there are these photons all around coming from various sources. They collide with the chair, and the ones that scatter into my eye, those are the ones I see. And what happens in my eye is there are these cells sensitive to the energy of the photons, and there are 3 different kinds of cells, each sensitive to a different kind of energy, not at a very precise value, but a range of energy, let's say. And depending on which one of these cells absorb this photon, converting the photon causes a chemical change which creates an electric current. Depending on which cones create this electric current, which one or which ones, it might happen that more than one is stimulated, so more than one creates a current, then there will be different electric signals. My brain interprets it as saying that, okay, that is blue. So first there is a directional information, depending on which cones, on which region of cones the photon falls, I know the direction. Secondly, there is a frequency analysis. At least I know my brain kind of interprets that range of photons to be blue. So that is a scattering process at the end of the day. So that is why scattering processes are, in a sense, the only thing that we can actually measure. So let's look at this classical problem. Now I send a particle at some impact parameter b, it scatters by an angle theta. If, let's say, my particle was not at the impact parameter b, but slightly higher, then it would scatter by some smaller angle. If I change b by b plus dB, let's say, my scattering angle will change by d theta. Now, my detector will be somewhere over here. Or I can move, I can just put many detectors, just pick one of them. So I can ask this question: what should be the area that I should target such that my particle will scatter into my detector? Yes, just imagine, this is the target, this is your target. If you aim to this point, it will scatter in that direction. If my detector is over there, it will be observed by the detector. If I target a point above, a region above, it will scatter less, so it will miss my detector. If I target in this area, it will scatter in this way, so again, my particle will miss. So this is the question. The detector, well, it has an area. It is at a distance r. There is a solid angle. This is the solid angle. Covered by the detector. So this is the question I would like to find the answer of. Let me call the sigma. This is the cross-sectional area. Which is the area such that if I target this area, the particles will scatter to my detector. Well, classically it's easy to measure. Let's do a simple example. Let's say a solid sphere. Now this is probably the simplest example we have. This is the central region. If my impact parameter is, let's say, B, it will hit my sphere at this point. Well, since it's a solid sphere, it will just bounce with the same angle. So if this is phi, this is also phi. What is the scattering angle? Well, the scattering angle is the angle it makes with the initial direction. This is theta. So theta is just 2 pi minus phi.
Pi minus 2 phi.
Pi minus 2 phi. So if my impact parameter is between B and B plus dB, then the scattering direction will be between theta and theta plus d theta. Now I have to find some kind of a relation between those two. Well, let's see. This angle over here is also phi. And sine of phi is B over R. Remember, phi is B over R is equal to sine of pi over 2 minus theta, because this is my phi. No, sorry. Pi minus theta over 2. Or cosine of theta over 2. Or B is equal to R times cosine theta over 2. dB is minus R over 2 sine of theta over 2 d theta. Well, this minus sign basically tells me that if I increase B, the scattering angle decreases. Now, that is what we expect. If you increase B, theta will decrease. That is the meaning of that minus sign. Now, let's say this is my sphere, and I'm looking at it from the top of the screen. So if I target this area, this is B, this is B plus dB. If I target that ring, it will scatter within theta and theta plus d theta. Phi angle doesn't change. So if I want to, if my detector has a given phi direction, so I should also aim the same phi direction. So this is, let's say, d phi. Now, d sigma is just this area. So if I target that area, my particle will scatter into a direction determined by theta plus, within theta plus d theta, and within phi and phi plus d phi. So that is my d sigma. And this d sigma is b d phi. You see, this length is b d phi. This length is dB. So the sigma is, well, let me use the minus sign, keep the minus sign also, minus r over 2 b sine theta over 2 d phi d theta. What I did was, this is my definition of d sigma. I already have determined that if I target within that area, it will move in the given direction. Then I know how dB is related to d theta. I just substituted it into the definition of d sigma. So let me write it slightly differently. This is minus R over RB over 2. Sorry. I should also substitute B. This is B. So B is R cosine theta over 2. So this is minus R squared over 4 sine theta d theta d phi, or d sigma is minus R squared over 4 d omega. D omega is the solid angle. No, I didn't forget it. You see, there is the cosine theta over 2, sine theta over 2. If I multiply that, that gives me sine theta over 2. Sine theta, 1 over 2 times sine theta. Well, let me drop this minus sign. As I said, it just means that if I increase d, theta decreases. The further away you go from the center, the smaller the deflection will be. I can calculate the total cross-section. It's just the sum of all d sigma, which is R squared over 4 d omega. But the total solid angle is just 4 pi. This is pi r squared. Well, that is not a big surprise. Remember the definition of d sigma. It was the area that I should target, such that if I target within that area, my particle will scatter in some direction. The total cross-section just tells me the cross-section, the area I should target, such that if I target within that area, my particle will scatter in some direction. I don't really care which one. In some, it will scatter. Well, that's not a big surprise. This is a sphere. The cross-section of the sphere is just pi r squared. If I target within that cross-section of the sphere, it will definitely scatter in some direction. Okay, this is the classical idea of the cross-section. Of course, this derivation, let's say, you cannot apply in quantum mechanics. Main reason, one of the reasons is, well, the uncertainty principle. If I determine B, I have no idea about what the vertical momentum is. It can be moving in any direction. Or if I know the momentum, I don't know the impact parameter. So this definition, this classical definition does make sense in classical physics, but I cannot generalize it to quantum physics. Even if I could, you see, if you are trying to apply this concept to particle physics, I mean, particles are very small objects. You cannot really aim them at a given point. You see, here I am assuming that I can actually aim my particle very precisely to some area and then measure the area. Well, that won't be practical for very small particles. What I would in general do is I will just send a bunch of them at the same time. It's alternative definition. Alternative. Let's say that here I have some target. And I will be sending many particles. Now this target will be made up of many potential sources. Just imagine doing this experiment with atoms. Every atom, let's say that among all these particles, if I put my detector somewhere over here, again keep in mind that this will be very far away, near each one of these atoms, there is a very small area this is my d sigma for each one of the atoms. If the particles that I'm sending, the particles in my beam, coincide with one of these areas near my scattering centers, then they will scatter towards my detector. Of course, here assuming that the cross-sectional area of each one of these scattering centers is not influenced by the presence of other scattering members. But as long as you are doing nuclear physics, working at nuclear distances, this is a safe bet that the nuclei are very far away from each other. So then the question is, how many particles, what is the flux of in my detector?
Çok yaşa.
Well, let's see. I know that this beam has some area A, some cross-sectional area A. The total area that I should be aiming at, let's say that these are A kind of particles, these are B kind of particles. Let's say A, this has thickness, let's say, let me forget the thickness for the time being. Let's assume that I have rho B is the density of B kind of particles. Okay, this is the X. Then within the targeted area, I have this much B particles. This is the number of B particles in the targeted area. Well, each one of these targeted B particles have a very small area nearby, such that if my incident particles reach that point, it will scatter in my detector. So this is the total area such that if an incident particle hits this area, it will scatter into my detector. Well, what is the fraction to the total area? So this is the fraction of the area such that if my particles hit this fraction of area, they will scatter to the detector. But this fraction will be the same as scattered particles to the detector over incident particles. Well, A is basically cancelled. So any questions up to here, by the way? What I'm actually doing is, let's say that each one of you has this area near you, and I'm sending well, in this description, I'm assuming a uniform beam of particles. Some of them will hit this area in your vicinity, and they will reflect to my particles. What is the total area that will deflect my particles into my detector? What's the fraction? This is the total area. And this is the fraction of that area to the total one. This is the fraction of the total area that will scatter into my detector to the total area that my beam is targeting. Of course, some of your particles will hit this area and it will scatter to my detector. Some of them will hit some other area, it will scatter in some other direction. So any questions up to here?
I even forgot what I knew from 548.
Okay, that is why I'm repeating it. Some of you didn't even take 508.
You can also write this in terms of target particles, right? The density of the. So this final expression we have, cross section depends on how many particles you throw in at the scattering source and the size of your detector relative to the total space. It should also depend on the
Well, let's see.
density of the target, right?
Yeah, the incident particles depends on the density of the particles. You see, the incident particles.
Sorry, I don't follow. Incident is the.
Let's look at it this way. Let me rewrite this. What are the particles? Particle flux into my detector. Let me look at this one. Well, this will be particles to my detector. Let me divide by time, per unit amount of time, which is 1 over, what is the, now this will be incident particles divided by time, this time, times rho b dx d sigma. What is the incident particles? Those are the incident particle flux times A rho b dx d sigma over time. No, time is already there. What is the incident number flux? Well, the density, whatever the density they have, times their speed, a kind of particles, times rho b. This is the total number of targeted B particles, times d sigma. So now I can extract d sigma, which will be particle flux in my detector. In particular, for example, okay, the nice thing about being a theoretical physicist is I can say that I have one B particle. That I have one particle, I'm just sending all these particles. Divided by, and I'm saying that rho A is also 1. Or no. Particle flux into the detector, particle flux into the target. Where this is what I mean by particle flux is rho A VA.
Not what I was asking. What I was asking was whatever the density of targets in the target, number density of scatters is.
You mean this one, MB?
Sure, that's the number of scatters.
Yeah. A is the number of incident A is the incident particles, B is the scatterers.
Right, okay. So in fact, it's included in it.
To simplify, I just said NB equal to 1. Now, the nice thing is I can now make sense out of this expression because I know how to calculate flux even for a wave function. So that will be our purpose. You see, we had calculated the density before. I don't remember the coefficient now. It was I over 2 phi gradient of phi star minus phi star gradient of phi. I think it was something like this. I might be missing some coefficient. So if I determine the wave function, just look at it from quantum mechanical perspective. If I know the wave function, well, I can calculate the flux. I know the incident. I can calculate the incident flux. I can calculate the outgoing flux in a given direction. Just take their ratio, and that will give me the cross section. Well, let me just make one correction here. Flux is the number of particles per area. So particles to my detector divided by the area of my detector. So this is area of detector. Okay, this is the area. D sigma is the area of detector times all that thing. Because area of detector will be r squared d omega. So now this allows me to calculate d sigma over d omega is the ratio of flux times that r squared factor. Well, that r squared factor is something we want because the flux, if you have a scatter over here, as you go further away, the flux will drop as 1 over r squared. So that is why we have this r squared. So that will cancel that dependence. So that will be the strategy. Somehow calculate the flux. Now, if we have, let's say, one particle, if we are talking about just a single particle, then the flux will be just the probability. You just send one particle with some probability it will scatter in this direction, with some probability it will scatter in some other direction. So this flux will be just measure of probability in that case. So we will be calculating the probabilities. Now, we can do this computation in a time-independent framework. That is basically what we had done in the last few days, in the last few weeks. Well, how does this work? I mean, this is a scattering process. Things change with time. Why does the time-independent framework work? Well, basically, just imagine this way. You have a scatterer. You are sending particles, which are plane waves. Just imagine that you keep a constant flux of plane waves, constant flux of particles. You are sending them constantly. Some of them will scatter from the scattering center in various directions. From a wave perspective, you are sending, this is the scattering center, you are sending plane waves. You have a plane wave component. And the scattering will create spherically outgoing waves. Since you are sending a constant flux of particles, there are a constant flux of outgoing particles, so this system doesn't change in time. Well, then I can use a wave function for this system. A time-independent wave function, because my system is not changing in time, so I can actually use time-independent wave function which will satisfy this equation. For quantum mechanics or for one particles, we are looking for solutions of this equation with the condition that when R is much, much larger than the range of my potential, away from the range of my potential, I should have some normalization constant, e to power I k incident times R plus some f of theta e to power I k R over R. This is what we are looking for. This is the boundary condition for my solutions. And the sigma, the omega, if you calculate the flux, etc., turns out to be f of theta squared. Now, what is although here there is no time dependence here, but if you look at from a time dependent perspective, I am sending these plane waves. So although this wave function is time independent, we identify this component, plane wave component, by the initial wave function or the initial state. We identify this component as the final, as if there's some time dependence. But within this framework, there's no time dependence. Now, in the next hour, we will start the time-dependent case, time-dependent treatment of this process. In that case, that initial will actually be the initial state, the final will actually be the final state.
Why there isn't 1 over R, term in the second term?
Well, that's a spherical plane wave. Not a plane, spherical outgoing wave. You see, just like e to the power I k dot R is a plane wave, e to the power I k R over R is a spherically outgoing wave, minus I k R over R is the ingoing wave. That solution satisfies this equation. But this is nothing but the Schrödinger equation if you multiply with minus h bar squared over 2m, no, sorry, not 0. This should be valid. It satisfies the zero-free Schrödinger equation, just like the plane wave.
It's 4 hours or 548, nothing will lecture, so.
Any questions?
John, what was the condition that small r must be done without huge?
Well, this is the range of the potential. Because if your potential just is non-zero within this region, outside your region, the potential is 0. So your whatever wave function you have it should satisfy the free Schrödinger equation outside this region. This is the general solution of free Schrödinger equation with the boundaries consistent with my boundary conditions. So out of my region, sufficiently far away, this should be my solution. And that f theta turns out to determine the scattering cross section. How? Just take this wave function. This is from this initial plane wave, calculate the incident flux. This is the outgoing wave. This is the scattered flux. Take the ratio, you will see that this is the cross section. You should do that as a review of quantum mechanics. Let's give a 10-minute break, and then we will continue.